thought I'd give you a quick update on where my motor project is. I started off with using a dual bridge motor driver, the ST6207, and that has got a nice data sheet online and a good app note. Here's a little perf board that I built up for that project, and it worked pretty much the first shot. I think I had some trouble with the sense resistors, but that was about it. I was originally using it for this project to drive the stepper motor. It's just a bipolar stepper motor, 4-wire, and a little encoder on there. And basically it's an 8 to 52 voltage supply. I was running at 24 volts. You can handle 2.8 amps, and there's overcurrent, and there's also a constant T-off pulse width modulated current control for each of the bridges. So pretty cool. Ball capacitor, as with most of these things, you want to have some decent caps with low ESR. That's what I've got there, 247s at 63 volts each. Again, the ESR controls essentially the ripple voltage, so you want to get some decent caps in there. And long leads are not recommended because they'll slow the charging time. And these guys, the way it works is they will be charging in the off time of the pulse width modulated output and depleting or being drained in the on time. So this frequency that you go at and that amount of charge that you can get over a long lead could be a problem. So you want to make sure your leads are as small as possible. It has, like I was mentioning, sense resistors. It has sense resistors connected in, and essentially those go into a comparator, which allows you to set up the turning on and off with a reference. And it also has a masking time built in and a one-shot monostable that goes into the gate logic, which drives these FETs, internal bridges. And what that does essentially is make sure that you don't have any run-through where both FETs are turning on at the same time. You have a blanking or a masking window in there. So a very nice feature. Worked out really well. No issues using it that way. The sense resistors are simply calculated by 0.5 of a volt over the peak current, so 2.8. Don't use wire around resistors on this because they'll have inductance. So you want to use metal film resistors for so you don't have any slow response or lag time introduced by that. But metal film worked well for this. I had to parallel a couple up because I didn't have the right values. They were, I think, half ohms in my circuit. I can't. It was something small. And then reference pins, again, the only trick with that is keep a cap on there. You want to put a couple of decent caps. I used 68 nanofarads close to the reference pins. You can't leave them unconnected because then of course that comparator will not work so well, and guess what? You won't be turning your thing on. The other cool feature has a charge pump built in, so what that does is essentially it's oscillating the output at 600 kilohertz, and you can set up a diode voltage doubler circuit basically. So what it equals is the voltage supply plus 10 volts from this charging circuit, of course minus the diode drops, so 1.4 in there in my case because I used IN or 1N 4148s on there, two of them, 4.7, and so that gives you about a 10 volt boost roughly, or 8.6. And plus the voltage supply, which in my case was 24 volts. And why that's important, because you have a bridge, it's built of all N channels inside, and if this is off and this motor can float up to the voltage supply essentially, then in order to switch this guy on, your gate has to be more than your source. So giving you that 10 plus volts there, or 8.6 or whatever plus volts there, more than the 24 of the supply, will allow that guy to turn on. So that's why having the charge pump built in is a very cool feature. Input circuitry is pretty straightforward. You got an enable bit, which is nice, and then your inputs. The enable bit basically allows you to turn this thing on and off even if you have inputs going to it. So for my purposes, it basically was just another bit out of the compiler, but it worked well with just the ons and off. But I could see that being useful if you have some external circuitry to shut it down. Also internally, it's got ESD protection, In thresholds, there's 1.8 volts for on and 1.3 for off. So a 3.3 volt microcontroller could still use this thing, but it is TTL. It's got the ESD for 2.2K, and they're not recommending series resistors in the input path because it could help introduce noise into the pins. And again, the inputs can't be left unconnected. The enable circuitry, actually, the control circuitry for overcurrent, basically shuts this thing down internally by using the enable pin. So you can do it externally or internally, it will also do it. So if you want to have some other scheme, they give you that pin, which is quite handy, although I didn't use it for my application. And the input circuitry, basically it pulls the pins down to ground on the inputs there if anything happens from an overcurrent perspective. There's some rules about the enable. You need a series resistor on it. It has to be 2.2 K or higher, and a capacitor needs to be connected to ground, so to reduce the output current when the overcurrent conditions exist. So remember, they're shutting this off internally, so you have to provide that cap and resistor. And again, you can't leave that unconnected. And the output, we talked about the bridge circuit with some gate drivers, all internal. It also has 2 constant off-time pulse width modulated controllers, so you can make use of that with your motor. It's automatic. You don't have to think. It's done for you. Basically, as the current load increases, the voltage across the sensor resistor increases, and when the voltage drops across the sensor resistor, voltage drop across the sensor resistor becomes greater than the voltage at the reference input. The comparator triggers the monostable, switching the low side MOS off. The low side MOS off remains off for the time set by the monostable, and the motor current recirculates in the upper path. So I've got a picture back here, so you'll get current circling here, and these guys will stay off. And when the monostable times out, the bridge turns on again. So the example circuit that I've mostly copied is this one here, and they show their sensor resistors, their bypass caps, the charging circuit, and their reference voltages, microcontrollers here. And in my case, I'm using a DSP PIC 2010. So yeah, this is what I've got going now. I've got essentially a discrete bridge built up, and come on, you can focus, and it's being driven by the PIC over there. A little power supply, and relatively straightforward. This is the mess that's happening here. This is my motor that we took out of the blender. There's the encoder on the end, and I've got the little breadboard model up here. A couple goofy things. I've got a big series resistance there just to get my 5 volts through a little surface mount chip on the bottom. I've got my bridge built up in here with some heat sinks, and there's the PIC down there. Big bulk decoupling for the front end. I've got a little interface panel here, 2 push buttons, and an LCD, and a fan right now cooling the my heat source, which is my resistor. And then this is going to the motor driver output, and I've got a little relay. This is a universal motor, so in order to reverse the motor direction, you have to take off the brush winding, because it's in series with the coil winding. So you have to basically take that lead, throw it through a relay to either go to this side or the other side brush. And by flipping the brush or the coils, one of the two, but only one of the two, you can reverse the direction. So that is the setup. I'm using the CCS compiler to write some logic, and right now I've got a basic program in there to take a push button and just flip the direction. I'm working on putting a little bit more intelligence into the thing, but that's where it's at right now. Okay, so here's where it starts with. When I fire it up, basically I've got 2 buttons here, one for forward, one for reverse. You can hear the fan running there, and basically, so if I push this button, I can basically, as long as I hold it, it'll ramp up. Now obviously I got to hold my encoder a bit better as vibrating, but that's going in the clockwise direction. Counterclockwise direction, and then this is going in a clockwise direction. And it will go faster, but it starts to move on me, so it's not being held right now. And then on the LCD, I'm just showing the hex value of the encoder reading. So as I go up, you can see it decreasing and increasing. And I got a couple LEDs on here to indicate I'm pushing the button. The idea will get a little more complicated as time goes on, but the idea is I want to be able to do two things: dial in a percent turns, so I will say encoder go from 10 to 20, and I also want to have a manual mode, which is what you see now, where I can just push it and slowly raise and lower this thing. But that's it for now.